In this video we're going to look at a quantity known as the second moment of area, or I, that occurs a lot in structural engineering analysis. Most commonly it occurs in the moment curvature equation, as shown there. This is an equation that links the bending moment in a beam to the curvature in the beam, or how bent the beam is. And it's used, for example, in calculating deflections of beams or buckling loads of columns, so it occurs a lot. What it says is that the bending moment is proportional to the curvature of a beam with two constants of proportionality. The first one is E, the material property, or Young's modulus, which is straightforward. And the second one is a geometric property, or I, the second moment of area, which is what we're interested in here. I is a property of the cross-section of the beam. So if you sliced through the beam and looked at the shape of the end of the beam, I is associated with that shape. And of course, if we have beams of different shapes, then their bending behaviour will be different. So I needs to capture this. It's probably best to look at an example to see how this works. If we imagine the cross-sections of two beams, as shown there, then we need to establish a measure of how they're going to behave when we bend them. Clearly they're going to behave differently. The one on the left will be much more flexible than the one on the right. Now, one approach might be to say, okay, we're going to look at the area of each of the beams, and in these cases it's very easy. We can see the area is 32 grid squares in each case. But if we wanted to express that mathematically, what we could do is say each of the little pieces of area is dA and has a value of 1, and then we could say the total area is the sum of all those little pieces of area, or mathematically we'd write that as an integral, as given. If we evaluate the integral, then what we find is we add up all the little pieces of area, which are each a value 1, and we get 32 in both cases, which is what we know intuitively. Now, clearly this cross-sectional property, the area, isn't what we need here, because we know the beams will behave differently when we bend them, but the area is the same in both cases. And so this is where the second moment of area comes in. And so if we define the second moment of area as that integral, so it's the integral of y squared times dA, where y is the distance of a piece of area from an axis. In the case of beam bending, we take the axis as the centroidal axis of the section. If we evaluate that, then in the first case, what we get for the little piece of area is a 1 squared, because the y is 1 in this case, multiplied by 1. And then, of course, we'd have to add up all the similar terms for each other piece of area. In the second case, however, the small piece of area has a y value of 3, so we end up with 3 squared times 1. Or in other words, that piece of area has 9 times as much importance for the second moment of area as the one in the first case. And if we did the full evaluation, we'd get very different answers for these two beams, which is what we're looking for, because we know they will bend differently. And so this is where the second moment of area or why the second moment of area is useful. It gives us a measure of how resistant to bending a cross-section of a beam is. And the key point is this y squared term in the definition, because it gives a lot more weight to material that is far from the axis about which we're bending. And so it's a measure of how dispersed about the axis the area is, rather than simply a measure of the area.